Hello, good afternoon. How are you doing today?
Good, thank you.
Good. All right, so starting this lab, you probably have noticed our lab will be a little bit behind our lectures. So we'll have to spend a little bit of time to talk about these concepts. These concepts some of them may have already seen in your lecture course. For example, probably have already mentioned kinetic energy in your lecture. But the momentum, I don't think any of our classes are that fast. So we just have to introduce these concepts so we can use them in the lab. But our lecture should be talking about them soon in a couple weeks. Okay, so here we're looking at some conserved quantities, including momentum and kinetic energy. So first, let's introduce a concept called linear momentum. Okay, now this is not this is a word you probably used in daily language or are very familiar with. You're saying, oh, that thing carries a lot of momentum. So you can kind of see, that if something is moving really fast, you would say that carries a lot of momentum. Or if something is big, has a big mass, then it probably has a large momentum, right? So we can use our intuition of that to help us understand what momentum is. And physically, it is defined to be the mass of an object times the velocity of an object. So m times v, that's momentum. And it's also a vector. Momentum is also a vector because its mass, which is a number, times velocity. Velocity is a vector, right? So then overall, you get another vector for p. That's the symbol we use to represent momentum. In terms of the units, and you can just do a dimensional analysis where the unit of momentum is going to be the unit of the mass times the unit of the v, right? So put a little square bracket over the quantity, meaning that I'm looking at its dimension or I'm looking at its unit. So the unit for mass is kilograms. The unit for velocity is meter over second. So when you add them together, you can also rewrite that using Newton's times seconds, because Newton is 1 kilograms meters per second square. This we know from Newton's second law, F equals ma, right? So you can write the units for momentums in these two different ways. And if you have a system that has many objects, each of the objects have a different momentum. Now the total momentum of the system will be the individual momentums added together. So this is momentum behaves like forces. When you have multiple forces, you simply add them together, right? This is a vector addition. We use the head to tail method to add up vectors, right? So for example, if you have one vector going this way, one vector going this way, then A plus B give you C. So C is A plus B. So momentums are adding up together just like how you add up vectors. So P1 plus P2 plus P3 can be added up like this. And conservation of momentum in the scenario we are looking at in our lab is when there are no external forces. Meaning that, what do I mean by no external forces? For example, if you have an explosion, right? You have, let's say, a bomb that splits into two pieces, exploded. Well, yes, there are a lot of forces, but that's all within the bomb. That's not an external force on the bomb. So the momentum of the bomb should remain a constant. So eventually nothing happens, the momentum is zero because it's staying at rest. Then you can see two pieces, one flying this way, one flying that way. So each of the piece will pick up a momentum, but because they are in opposite directions, when you add the total momentum of those two pieces together, it's still going to add up to be zero, just like when it was before it exploded. right? Another way to think about no external forces, when you have a cannon, it shoots out a bullet, and then the body of the cannon would recoil. Again, because of the bullet and the cannon, overall as your system, there's no external forces on it, right? So if one part of the system moving this way, the other part have to move the opposite way. Also, you can think of someone standing on the boat, right? While they start walking on the boat, then the boat goes the other way. So you can view the person and the boat together as one system. So there's a force within the system are considered internal. So the opposite of external is internal, and that force does not change the momentum of the system. So the momentum of the system remains a constant. So this is simply saying that the momentum does not change and remains a constant number, constant vector. Okay, and this is what we're going to evaluate in the lab by looking at two different cards. We have a relatively smooth track, so it's reasonable to ignore friction, although it's not zero, but we are just going to make an idealization saying because the track is smooth enough and friction is negligible, then the momentum of the two cards together should remain a constant. That's what we're going to evaluate. There's another quantity we have probably already talked about in your lecture. That's called the kinetic energy. So this type of energy, we're all familiar with energy, right? You have the solar energy, we have the batteries, the chemical energy stored in the batteries, and you use electricity. You have energy of the food that we eat. And so kinetic energy is a type of energy that's associated with motion. Whenever you have something that is moving, have a velocity, you have kinetic energy. So kinetic energy is 1/2 times mass of an object times the velocity of an object squared. So that's kinetic energy. It is a scalar. So kinetic energy is not like momentum. Momentum has directions. Kinetic energy is only a number, doesn't have directions. Okay, so when you have multiple part of the system, you simply add up all the kinetic energy together, you get the total kinetic energy of the system. So you have one card, right? You add the kinetic energy of the one card, and you have two cards, you add all the kinetic energy together. Looking at the units for the kinetic energy, we do the same thing as we did before. The unit for kinetic energy is the unit of the right-hand side, 1/2 mv squared. 1/2 is a dimensionless quantity. It doesn't have any unit. So the unit of that is just 1, right? It doesn't change whatever units you're gonna have. And mass will give you kilograms, and velocity will give you meters per second. So it's velocity squared, so meters per second squared. So overall, you get kinetic energy has a unit of 1 kilograms meter squared over second squared. And we also call that a joule. So that's 1 joule. So what you're familiar with the calories we talk about in food is also a type of units for energies. So there is a conversion between how many joules is 1 calorie. So you can convert between these two different units. So they're all units. Joules are units to describe energies. Okay. We are not going to do a potential energy in this lab, but I just want to briefly mention that what we call mechanical energy is the kinetic energy and the potential energy together. So potential energy, as you probably have already talked about in the lecture, if not, it should come up real soon, has to do with an object on Earth. If they have a certain height above the, let's say the ground level, then the object and the Earth will have this potential energy, gravitational potential energy. Meaning that, well, if the object falls down to the ground from that height, it's probably going to have a very fast speed. It's probably going to do some damage, like will punch a hole on the ground or something, right? So it certainly at a certain height, this object and the Earth system will have this gravitational potential energy. So that you only need to consider the potential energy when you have a change in the height. So something going up or down. In our lab, everything happening on the horizontal track, nothing is going up or down. So all the energy we're considering is the kinetic energy. So we will just do conserved quantities for two. One is momentum and one is kinetic energy. We're going to measure these two quantities for the lab. Okay, so before I go ahead and talk about what we have for the lab part, I wanted to pause for a little while and see if there are any questions regarding these concepts, kinetic energy and momentum. Are there any questions on these two concepts? Okay. All right, so let's also use our pre-lab to further clarify these concepts, and then we will look at the procedures for the lab. So let's take a look at our pre-lab. So it's very similar to the actual lab we're doing, but we have some concrete numbers to work around with. So this is just to get us familiar with how to calculate these individual terms. Okay, so part A of the lab is a bouncing collision, meaning that when something hits something, it bounces back. Because the cars have a magnetic end, right? So they can never really touch each other. So when something bounces the other car from the magnetic end, this car will bounce back, the other car will continue to go forward. As opposed to the second part of the lab is a stick collision, that they have the Velcros and facing each other. So one bounces in another, they stick together and they move together. But now we're looking at the bouncing part. We have cart 1, the mass is given with a initial velocity that is given, hitting a stationary cart 2. It was originally stationary, and the cart 2's mass is given. After the bouncing collision, car 1 bounces back, and the speed to the left is given. Okay, so this one is 1.5. This one was at rest. This one bounces back, 0.9, and this one continued to go forward now with 0.6 meters per second. Okay, and the positive x direction is defined for us, is to the right. So now let's look at these different terms together. First one, what is the total initial momentum of the two cars? Here, our two cars are our system. So for the two cars, the red and the blue car, the initial momentum of the system, how do I calculate it? Is car 1 initial, so P1I, plus car 2 initial, P2I. Okay. Now, these are all vectors, so the correct expression should be with a vector sign on all of them, right? So you have two cars, the total momentum is the car 1 plus car 2. Now let's expand this in the x direction because everything is moving in the x direction. So I can get rid of, in my next step, I can get rid of these vector signs, okay? So car 1 is moving to the right initially. So how should I write the initial momentum of car 1? So how should I expand P1I? Anybody have any thought?
M1 V1.
Okay, M1 V1, very good. And it's initial, right? V1 initial, so I'm gonna add 1I as the subscript. Very good. And then P2 will be very much alike. It will be M2V2 initial. Okay, so you know M1, that's given. And do we know V1I? Do we know what is the initial velocity of car 1?
1.5.
Simply 1.5. And here you can see I simply said positive 1.5 because it's already moving in the positive direction. So I've thought about the directions and I claim it's positive because I've defined a positive to be right. Now car 2 has a different mass and initial velocity of car 2 is that given to us?
No, it isn't. It would be 0.
Right, it's have a no number, but it's stationary, meaning that before the collision happens. So initial means before collision happens. It's 0, it's staying at rest. So this one is 0. Now really, you can just get your initial momentum to be 3 kilograms times meters per second for the 2 cars. Now, that's the first part. The second part, final momentum, very similar. P final again is P card 1 final plus card 2 final. Again, we will get rid of our vector signs by considering all of these in the x direction. So again, you expand P1 final using M1 V1 final plus M2 V2 final. Final means after collision. Collision happened already. So M1 is the same 0.2 kilos. So how should I represent my V1 final here? I would write V1 final as how many meters per second? What are your thoughts? How do we write V1 final here? Joshua said negative 9.9. Very good. It's negative 0.9. So here, be very careful. Not only you wanted to consider its magnitude, you need to see it's in the opposite direction of the positive direction. So you have to put a minus sign on it because that momentum are vectors, right? If you don't put a negative sign here, you would get a wrong answer. And then I'm going to put in the velocity for car 2 final, which is after collision. After collision, it's 0.6 meters per second. And is that positive or negative? It's moving to the right. So that's positive. Okay, so positive 0.6 is good. And you could put these together. This is similar to what we do in the lab. We measure the initial velocity, we measure the final velocity, and then we add them together to see if the initial and the finals are indeed equal. They're not going to be exactly the same because in the labs, you have some errors in the measurement. You still have some kind of a little bit of friction that slows the car down. But overall, roughly, they should be equal to each other approximately, okay? So you can see this is negative 0.18 plus 0.48, and it add up to be 0.3. Okay, did I make a mistake there?
For part A, I got 0.3.
Right, so yes, thank you. They are equal, as you can show that the initial and the final momentum of the two cars are the same for this bouncing collision, okay? So that's 2A and B. For kinetic energy and final kinetic energy, okay, so let's do part C. together. So kinetic energy initial is again the first card plus the second card. Okay. First card is 1/2 m1 v1 initial squared. So here I'm simply using the quantity, the definition of what a kinetic energy is. And it is 2 initial. It is a scalar, so I don't have to worry about the directions. It has no directions in terms of the energy. So this is 0, and plug in the numbers for the masses. Sorry, 1.5. Yeah, plug in the velocities, and then you can calculate this kinetic energy. Something like that. And for final kinetic energy, very similar, but I just wanted to highlight one thing is the final kinetic energy for the cart. Sorry, let's just write here. Part D is the first cart, the velocity final squared, and the second cart, the velocity final squared. So for the velocity final, well, you can see that when we do the momentum, we use negative. Here you can see because it's a velocity squared, you can really just use the magnitude of this velocity. And also energy is a scalar. You don't have to worry about its direction here. So you can just use the magnitude of the velocity, which is 9.9 meters per second, instead of putting a negative sign in there. Now the second card is more also straightforward, putting 0.6 squared. Okay, so and you can find out the number to see if it's equal, mostly equal to the first part. For elastic collisions, bouncing collisions, you can see they really barely touch each other. So there hasn't been any kinetic energy loss during the collision. But if they stick together, you can see that give you a lot of energy loss. So part B is a sticky collision that they stick together and they move together with the same velocity. So part A is exactly the same as before. Part C is exactly same as before. It's really B and D we will do it slightly different. Okay, so part B, the final momentum of the entire system is again card 1 final and card 2 final. But because they are all moving with the same velocity, they're moving together, I can do card 1 and card 2 together, moving with the same velocity, V final. Okay, so they're added together. You can group the masses together because they become one piece. V final is given. It tells me, so this is this much kilos times 0.3 meters per second. So you can see that gives me how much? Again, 0.3 kilometers per second. So just like what I had for initial. Okay, so even though the collision type is different, one is bouncing back, one is sticking together, but if you look at the total momentum of the two cars together, the overall momentum still remains constant. It does not change. However, if you make a prediction about the total final kinetic energy of the two-car system, what is your prediction? Would you say the final kinetic energy the two-car has, is it going to be equal to the initial kinetic energy of the two cars? Or is it going to be bigger? Or is it going to be smaller than the initial kinetic energy of the two cars? Which one? So if you had to make a prediction, what would be your guess or choice? So would they be equal or larger or smaller? So if they were equal, I would probably guess that if you have a bouncing collision, it will be equal because the energy hasn't gone anywhere. They haven't touched, right? They did not have a collision. They're simply just being repelled away by the magnetic ends of the cards. But now what happened is they have a Velcro sticky parts. So as soon as one hit another, they stick and they move together. So in this scenario, do you think they would equal, or would the final energy be more or less than the initial energy? What do you think? Any thoughts?
I got that the final kinetic energy was greater than the initial, but I'm not sure how much sense that would make though.
Yeah, then if it is bigger, then you need to think about where would that come from, right? So the only way you get a bigger kinetic energy without changing the mass is if you make it move faster. But there's no other forces around this track to make them move faster. They're simply doing its own thing, right? If anything, you probably should get something smaller because you have a collision that lost some energy, and you have the track that's slowed down. The cars that should have a smaller kinetic energy. So if you were to look at sticky collisions, really the final kinetic energy should be smaller than the initial one. Okay, you can look at the mass a little bit more careful to see why if they were not the same. So to calculate the final kinetic energy, again, put M1 and M2 together because they are now one piece, V final squared. Okay. So M1 plus M2 is 1 kilos. The final is 0.3 squared. So you should get 0.045 joules, 0.045 versus 0.225. So this is much smaller. So this is much, much smaller than what you had before. Okay, so this is what you had before. All right, so that's our pre-lab. Any questions here before we move on to talk about the lab procedure? Any questions so far? Okay, all right, let's move on to switch back to our lab procedure. We have two cars. Part A, when we do a bouncing collision using the magnetic ends of the cars, we have one car bouncing into another, and after collision, they move to opposite ends. So the mass of these cars are already given because it's not very clear from the video. So if you have a hard time reading it from the video, you can use these numbers because it's already given.
Professor?
Yes?
Actually, could you actually do the kinetic energy for part B on the pre-lab?
You mean this one? You mean this one?
Oh, okay. So you did both of them?
I didn't do part A, the initial kinetic energy, because that's exactly the same as what we did in part A. So initial momentum and initial kinetic energy is just like part A.
Yeah, because it's zero, right? Because the second car ends up being zero.
Yeah.
Okay.
Yeah. So part C is the same as part C here.
And for part D, they're basically this. I just want to double check. They're basically the same, right? 0.225.
Yeah, they move together. So I put the total mass together multiplied by the velocity squared.
Okay, and that was just that's just like a coincidence because of the numbers, basically, right? Or not?
What's a coincidence?
Oh,
Oh,
I'm sorry. No, I mean in part A, the reason why they ended up being the same was just because of the numbers, right? For the not for the kinetic energy, but for the system, for the initial momentum and the final momentum.
oh, that's not a coincidence. That's exactly what we're trying to prove, this physics principle. That's like how we're proving Newton's second law. For physics, there is a principle says conservation of momentum. That is a universal law of nature, conservation of momentum, which says if there's no external forces on the system's momentum will remain constant. So that is exactly what we're trying to show. So we created a system of two cars and we make it have a collision in the lab. So we want to see, is it indeed true that the initial momentum of the cars remains constant? So we measured them initially, we measured them finally, and we want to show that they are indeed constant. And then, of course, this is a exercise, they're perfectly matching. In your actual data, they won't be like perfectly equal to each other, but they will be close enough. Does that answer your question?
Yes, that's really, thank you so much for explaining that.
Thanks for asking. Very good. Someone might be wondering about that too. Okay, so let's go back to our lab. This is the data table. Okay, so to measure momentum, we need the masses of the cars, which we can measure on the scale, which is also given because it's not clear from the video. There is a velocity of the cars. In our lab, we use a photo gate, the sensor. Whenever the car passes by, it triggers the sensor and you can write it down what the velocity is. So how many velocities we have to measure for this bouncing collision?
3.
3, very good. Initial, only one velocity because one of the cars is at rest. And finally, there are 2 velocities, so you need one sensor on each side. So you're gonna measure 3 velocities total. Okay, and then you will calculate the total initial momentum of the 2 cars, the total final momentum of the 2 cars. This is very similar to the pre-lab. You should be able to do this. You can look at a percentage of difference that reflects how accurate the lab has been performed, how good your data is. So you can use the final momentum minus initial momentum divided by the initial momentum. So if they are exactly equal, right, you get a 0% of difference. Well, that's very accurate. But probably you'll have a few percentage. If you have a few percent of difference, that's still pretty good. So let's take a look at that's our data.
Professor?
Yeah.
Really fast. The final value, initial value, that's initial momentum and final momentum?
Yeah, final value means the value for the momentum.
Right, okay. Okay, just making sure.
Sure. Let me take a look. Let me switch back to our video and then we'll watch how they have recorded the data.
For inelastic sticking collisions, we use the Velcro side. For the elastic bouncing collisions, we use the magnetic side. The magnets are mounted so that the same pole is opposing each other. We will set the number of triggers to 2. This will allow us to run a fun trial at the end of part A. We begin by testing for a level track.
Okay, so I just want to say the triggers is because they want the sensor to record 2 different velocities. So they simply set 2 triggers. And then for a few minutes they're doing here, they're gonna make sure the track is level. Just to make sure that if you have a velocity on the left-hand side of the track, it should be equally approximately the same velocity. You don't want the track to be tilted. So after they finish setting everything up to be as good as they can get, and then they start taking part A, the bouncing collision data. So we'll just do it like a practice to see if we know what to read from the data sheet. So you can see what they did. The blue car pass through the sensor on the right and make the and then the red car pass through the sensor on the left. Then at the same time, the blue car bounces back and passing by the sensor again, so triggers another data. Since that they set triggers for both of the sensors, the softwares, they need to use the hand to trigger the left-hand side of sensor one more time, just so that computer knows that, okay, now the data collection is over. They could have set it to 1. I don't know why they didn't, but that's how they set up for now. So I don't know if you can read a little bit more clearly from these data. So from this data, can anybody tell us what is the initial velocity of the blue car?
57.6.
Yes, very good. That is the first row on the right-hand side, the right sensor. Okay, very good. And what about the final velocity of the blue car?
15.5.
15.5, very good. The second row. Okay, excellent. What about the final velocity? If I say, do you know what to write down for the initial velocity of the red car? What would you write down?
Would that be 36.5?
I asked what is the initial velocity of the red car?
0.
It's 0, very good. It's not something.
Oh, right, because it's stationary.
Yes, for what you
Right.
had just read, 36.5. What kind of velocity is that?
Your final.
The final velocity of the red car. They have one extra data here, 55.2. Do you need to care about that one?
No, I think that's a second trigger.
Yeah, that's just a hand to tell the computer, we're done here, so give me the data. So you know which one, you need to know which is the right one to data to record. So in the data sheet, I had reminded you for the speed of the red car, use the first row of the data, not the second row. Second row is your hand. Okay, the kinetic energy is very similar. It's just the formula that you use is different. So you need to record the velocity one time, and then you can use the formula to write down what you need. Okay, and let's continue to look at our data collection. So they will do this many times. And, so eventually they finish this data collection for part A. So let's move on to look at part B. So never mind this part, they're bouncing the two cards together toward each other. That was just for fun. We're not using that data. So now is finally the sticky part.
Can you hold on for a moment?
I'm sorry?
Oh, I had a question. So in this experiment, the blue car still kept going forward a little bit after the collision?
Oh, in this part, you can see what happens. The blue car was stationary. The red car bounces into the blue car and they stick together and they move together. Okay, so was that clear?
But that's for part B, right? Or no?
Oh, that is for part B. We now go back to, we're not doing part B. I'm looking
Oh, no,
at,
I know. I was just asking about for part A,
Mhm.
like the final was, instead of being negative, like in the pre-lab, it had a positive number?
Oh, because the computer doesn't care about directions. The computer will give you positive values regardless. You are going to add the negative signs when you calculate the momentum. But that's a very good observation. That's a really good point.
Thank you.
Okay, so yes, you read all of these are positive velocities, as you noticed, but we want you wanted to be able to add the which one? For the green part A, which one bounces back? Oh, the blue car bounces back. So the second data you have read for the blue. Now you want to make that negative when you calculate your momentum. When you record the speed, it's still positive because it's speed. When you calculate momentum, you got to put a negative sign on it. So a very good observation. We do have to be careful there. Okay, so now let's take a look at that. Take a look at our part B. So again, you can see that they now have set the trigger to be just one trigger on the left sensor and two triggers on the right sensor. So here, the red car bouncing to the blue and they move together. So I'm gonna ask you guys, what is your initial velocity for the red car? What is the initial velocity of the red car?
Was that the data on the left side?
Yes, that's the data on the left-hand side. Very good. I wasn't
Yeah.
sure if I lost connection for you guys because I was somehow didn't see my Zoom window.
Oh,
Okay,
yeah.
yes. So the initial velocity for the red car is 48.5. The initial velocity of the blue car is 0 because it was stationary. Okay, now what is the final velocity of the two cars together after collision?
Is it 21.058?
Yeah, there are two numbers there, right? There's a 29.7 and the 21.1. Which one do we want to record?
21.1.
Let's see what happened. Which one triggers which one?
I think it's the second one because I think the first one is for the blue car.
The blue and the red are now together. They're one piece. So whoever triggered the sensor. So that's the 29.7 is when the two cars first pass the sensor. The 21, the next row is when the two cars, now it's two cars. It's a very long car. The front of the car passes the sensor, the tail of the car passes the sensor. So which one would give us better results? And if it's all the same car, why is it different? Okay, so I got Neil and Giovanni all agreed we should use the first one. So the first one is right after the collision, right? Because they click and they move past. As far as why the second one is a little bit smaller than the first one, any guesses? Because the second one is also two cars together. It's just the bars happened a little bit later. So it's the bar that's on the red car passing by the sensor later. Yeah, so it's because of it's still not completely smooth. There's still a little bit of friction in the car. So you want to be able to take the velocity as soon as you can right after collision. That is the most accurate one. So if you waited long enough, the cars would have been slowed down more dramatically and you would get velocity that's not smaller and it would not be as accurate. Very good, very good. Okay, so let's take a quick look at our data sheet, but that's pretty much all. Let me switch back to my slides. Okay, all right, so we have talked about these data you record, noticing that this is a positive value. Let's say if it's 40, right? Then when you calculate total momentum, you put a minus sign here. Okay, so be very careful. And kinetic energy is exactly the same, but you just use different. This is not updated. Give me 1 second, sorry. All right, just that the Zoom is a little kind of slow right now. Or maybe my computer is a little slow right now. Okay, so that's the kinetic energy. And the next part is the part B, sticky collision. You measure the velocity, the sticky collision, you only measure two velocities, okay? One on the left and one on the right. On the right-hand side, you use the first row because that is right after collision. You want to catch that velocity, not until they have already moved for a little while. Again, do the same calculation to do the percentage of difference. So for kinetic energy, potential energy, we expect initial and final. For momentum, we expect them to be equal for both type of collisions. For the kinetic energy, we only expect them to be roughly equal for the part A, bouncing collision. For part B, we know that there has to be some kinetic energy lost during the collision. So we expect a much smaller value for the kinetic energy after the collision, and your data should reflect that. Okay. All right. So that's all for we have for today's lab. Any questions so far?
Maybe just so for part A, when for the velocity final, you have to input negative, right?
You have to put a negative sign when you calculate the momentum. Yeah.
Right. Okay. Okay, for sure. Thank you.
Okay. Very good. Any other questions?
Yes. So at the beginning of the video, I think at the beginning of the video, they had they were talking about friction, and on the left, the sensor on the left side, it said that it was like 2.1 more, and on the right side, it said 0.9 below. So I mean, do we have to subtract that from the vehicles at all? No. Or add it?
Trying to level the track? Is that what you're asking?
Yeah. They were trying to level the track, but they didn't really make it like level still, because on the left side it was 2.1 off, but it was like 2.1 above what their number was. And on the right side,
okay.
It was 0.9 off, but it was below.
100% equal, because there has to be some kind of friction. All they were trying to do is to see the velocity here and there are approximately equal to each other, and then you can just go ahead with your lab. We cannot subtract or add that into the velocity we read later on. So we would just take whatever velocity the data gives later and just use it. Okay. Yes, there's another question for both momentum and kinetic energy. We find percentage of the difference the same way. Yes, we use the same way to find the percentage of difference. So the final value minus initial value divided by initial value. See how much percent of difference that is. Very good. Thank you very much for all the questions. If you think of any more, feel free to email me, and we will see you guys. I'll see you guys next Thursday. Have a good rest of the week. Bye, everyone.
Have a good day, Professor.
Thank you. Bye, Professor.
Thank you. Bye-bye.